Okay, so now that we've covered binary representation, ones complement and twos complement, let's talk a little bit about floating point numbers. Those are an interesting animal, okay? We're going to begin first of all by converting floating point numbers into binary. And the way that we do that is, let's say we take the number 169.9. What we're going to do is we're going to separate it out into its integer and its fractional components. Okay, so we have 169 here, and then we have the fractional component of 0.9. Okay, there are different methods for doing these kind of conversions, but they all require that we divide them out between their integer and fractional components. The book has a really good way of calculating these floating point numbers. I'll let you know up front, works great, okay? But there is another approach as well. So let's go ahead and let's use that other approach. You get to, again, choose what you like best, okay? So we come down here and we pick the successive division method, okay? The reason that I show you the successive division method is because we can easily write a program that will do this, okay? It's actually a little easier to write a program to do this than using other methods, okay? And basically what it is we start out with our number 169 and we divide it by 2, okay? Well, that happens to be equal to 84 with a remainder of 1, so we record 1. And what we're interested in is that 1. That's really important to us, okay? When we're interested in a remainder, we're performing what is known as modular arithmetic, okay? We don't care too much about this portion other than the fact that it tells us when we're going to end our little algorithm, if you will, but we are intently interested in all of these remainders. So 169 divided by 2 is 84, remainder 1. 2 divided into 84 is 42 with no remainder. 2 divided into 42 is 21 with no remainder. 2 divided into 21 is 10 with 1 remainder. 2 divided into 10 is 5 with no remainders. 2 divided into 5 is 2 with 1 remainder. 2 divided into 2 is 1 with no remainders. And then finally we divide 1 by 2, which is 0 with 1 remainder. The key is this critter right here. That lets us know that we are done. All right. So for those of you who really like to program, you have your stopping condition for what's called a recursive algorithm. Boy, I bet you that was exciting to hear those words, wasn't it? We'll learn just a tiny bit about recursion later on in the semester. All right. So what is the answer? Well, the way we figure out what the answer is we read these numbers from bottom to top. So the answer is 10101001. That is 169 in binary. Well, now that we've done that portion, we have to do the fractional portion. So let's pop on over to the fractional portion. And interestingly, the fractional portion, what we do is we do successive multiplication. All right, let me clean up this slide a little bit so that when I actually print the thing out for somebody, it'll look a little nicer. All right, so how does it work? We do successive multiplications. We're looking at 0.9, okay? What we're concerned about is what's on this side of the decimal point. That's what's most important to us. We don't care about this portion at all, okay? Until we finally end up with a 0 that's left over or something along those lines. But in any event, let's go ahead and let's run this multiplication out. All right, so we have 0.9 times 2 is 1.8. So I am concerned about the 0.8. So I'm going to multiply 0.8 times 2 is 1.6. 0.6 times 2 is 1.2. 0.2 times 2 is 0.4. 0.4 times 2 is 0.8. 0.8 times 2 is 1.6. 0.6 times 2 is 1.2. Are you seeing a pattern here? 0.2 times 2 is 0.4, and 0.4 times 2 is 0.8. So we have a repeating pattern that's going on here. The answer, unlike the other way where we read from the bottom up, this time we read from the top down, and the answer is a 111001100. And what we do is, focusing on the repeating pattern, when we write the answer down, we'll say 0.1, and the very first digit of the repeating pattern we'll put a dot above. So we have 1, 1, 0, 0, and we put a dot. And that's a little message to whoever's reading this answer that this just keeps repeating on forever. In other words, the number is irrational, right? Which means we can't get an exact result. This is really, really huge. This is the problem with floating point arithmetic. You cannot necessarily get an exact representation of your number inside the computer, even if the number is pretty straightforward, because as you know, we had 169.9. We didn't have any other digits that were in there, but in truth, we were unable to actually represent 169.9 exactly in binary. And this can be a problem, because what happens is a computer in a program may round things off on you when you don't want it to do that. Okay? So, huge problem. There are some floating point numbers that cannot be represented exactly in a computer. The last number, for example. Or if you want to, you can try 0.1. See if you can get that to be represented perfectly in the computer. And just a little bit of thinking helps you to realize that no, you're just going to end up with a repeating pattern. Okay? That being the case, you will always end up with an approximation. You'll never be able to get an exact number. So we have to come up with a solution for this. We have to come up with a solution. And there are a couple of solutions, okay? One of them doesn't work so good because we have to throw a couple of things in there that I don't really want to go into, but the other one does work, all right? So first of all, let's look at the first solution. Work only with integers. Never use floating point numbers, okay? Some of you guys are going like, how? How can we get rid of the fractional portion of our number? Well, one of the ways through what's called normalization. Normalization is the concept of saying, hey, in this circumstance it's normal. Inside a computer, integers are normal. So what might I do to a floating point number to turn it into an integer number? Well, the answer to that is just to keep moving the decimal point to the right until you have only integers left. This is huge, okay? This is a really, really cool concept. When you do that, when you choose to do that, though, you have to keep track of the number of times that you moved the decimal point and store that in a memory cell. So we have one memory cell that is holding an integer representation of our floating point number, and we have another memory cell that is holding the power of 10 for the decimal point, or the location of the decimal point. Okay? That's why they call them floating point numbers, because the point floats all over the place. And of course, I'm sure you guys, you folks were introduced to the notion of floating point arithmetic back, in the 8th grade, 7th, 6th, 5th, whatever grade that was, and you said, yeah, the decimal point moves wherever it needs to move in order to give us the number that we really, really need. All right? The other solution is to treat all numbers as fractions. So let's say that we have 0.9. Well, if we have 0.9, then that's really 9/10, right? We have an integer numerator that is 9 and an integer denominator that is 10. And later on down the road, I may show you how to do fractional arithmetic inside of a computer. But if you ever need to work with numbers that are absolutely exact, you have to normalize the numbers and probably use fractional arithmetic. Okay? Going the other way, if we want to go from binary into decimal, then it's real straightforward. It's real easy. The best way is just to simply use the power of 2 example that you find in the text. It's very straightforward. Shouldn't have any trouble reading that. Okay, so hopefully these videos helped you out a little bit as far as understanding the content of Chapter 2. So with that, I will say happy coding.